Well, we're going to look at some quadratic applications and a few more fractional equations. The fractional equations we look at won't be anything new other than the fact that when we clear the fractions, we get a quadratic equation to solve. They'll have more than one solution. Two main things that we want to take care of. We're going to solve some word problems that result in quadratics, and we want to solve fractional quadratics that give us quadratic equations. Basically, we're looking at word problems and fractional equations that can have more than one solution. That's what it boils down to. We'll use whatever technique kind of presents itself as the most convenient for these. And sometimes when you get your equation, one technique will just sort of be more clear than the other, or more lend itself better. Let's start out with a few word problems. Let's get those out of the way first. As with the other word problems that we did, oftentimes a picture is going to be useful. Most of the word problems that I've picked out are geometry problems. There's a lot of other types in your book. We're going to focus mostly on the geometry ones. So here's what we got. We got a window. It's 15 inches taller than it is wide, and we know the area is 1,204 square inches. And what we want to determine is what the dimensions are for that window. Okay. Well, what is the information? A window is 15 inches taller than it is wide. What's that good for? What can we do with that? 15 plus x, where you're calling x what? Yeah, let's just call the width x. Then we know in terms of x what the height has to be, right? The height has to be 15 more than that. So our width is x, our height is x plus 15. Agree with that? Okay. Well, then how do you find the area of a rectangle? Multiply these two together. You take the width times the height, and we have our area. So our area in this case is going to be our width, x, times the height, x plus 15. Well, we know what the area is. It's a good thing we know what the area is. We know that our area is 1,204, so we have 1,204 equals, we can distribute this, x squared plus 15x. Well, anytime you set up a scenario and end up with a quadratic formula, you know there's more than one answer to this. There's more than one possible solution. Now, they might not all make sense, but there's at least one numeric solution, or at least two numeric solutions. Exactly two numeric solutions, in fact. So let's solve this. Now, you've got your choice. You've got basically 4 tools for solving quadratics. You can graph it and look for the intercepts, which is remarkably inconvenient, and we will not do that at all today. You've got 3 methods left. You can either complete the square, which is also pretty inconvenient most of the time, which leaves 2 practical ways to solve. You can either use quadratic formula, or what's the 4th method? You can factor. Okay, so let's shift everything. Either case would require that they be set equal to 0. So this quadratic becomes 0 equals x squared plus 15x minus 1,204, and that's equal to 0. Now, take your pick. At this point, you got your choice. You can either factor that, or you can use the quadratic formula. Any recommendations? Ryan wants to factor it. All right, let's factor it. No, we're not going to factor that. Okay, so we know our values of a, b, and c. A equals 1, b equals 15, c equals negative 1,204. So the quadratic formula says x is equal to So in our case, we have x equals negative b. That's negative 15 plus or minus. b squared minus 4ac, that's 15 squared minus 4 times a times c all over 2a. Whoops, we know what a is. I'll tell you that that works out to negative 15 plus or minus the square root of 5,041 over 2. And so we get two solutions for x. If you work that out, you'll end up with x equals 28 or negative 43. Well, we got our two solutions. The width of that window is either 28 inches wide or negative 43 inches wide. What does our width have to be? It's got to be 28. So our window has got to be 28 inches by 43 inches. Now that's an easy one to check. 28 times 43, make sure the area is 1,204. It will be. How do you find perimeter of a rectangle? You do what? 2L plus 2W. You add up the length twice and the width twice. It's the distance all the way around, so that's equal to 2L plus 2W. Well, and in this case, we know that 2L, our perimeter, plus 2W, excuse me, 2L plus 2W, our perimeter, is equal to 104. Okay, well, that's useful information, but what's the other fact that we're given here? We're told that the area is 660 square feet. What's that? That's L times W, right. Now, this is technically what we call a system of equations. There's two unknowns. But we can very easily treat it as one unknown thing. Here's why. If we know that 2 times the length plus 2 times W is 104, let's divide everything by 2 and just figure out what the length and width is. What's the length plus the width got to be? It's got to be half that. So we can conclude from this fact, let's go down here, that if the whole distance around is 104, the length plus the width alone, and we're really just dividing each term by 2, the length plus the width is equal to 52. So if I told you this room was 10 feet wide, well, how long would it have to be? It'd have to be 42. If I told you that the width of the room, and we're looking at this fact right now, if I told you the width of the room was 10 feet wide, it would have to be 42 because the length plus the width have to add up to 52. So we can say that in general, the width of the room is equal to 52 minus whatever the length is. So we know the length times the width, but the width we know to be 52 minus L has got to be equal to 660, where 52 minus L is really our width. Okay? That's an example of system of equations. That's the next unit that we're going to do, but we don't have to know much about system of equations to get this written in a quadratic form. We just have to recognize these two facts. So we'll kind of perceive, even though we haven't formally studied systems of equations yet. Okay, now that's the setup, and like most word problems, the setup is where the trouble arises. But does the setup make sense in this one? Does it look okay? Okay, well then we can go ahead and solve this. We get 52 minus L squared equals 660. 52L, thank you, yep. So let's bump those over to the right side, and we get 0 equals L squared minus 52L plus 660. Again, you've got your choice. You could factor that if you want to. Good luck. But I think it's more practical to use the quadratic equation. We know that L equals negative b plus or minus the square root of b squared minus 4ac To work that out, you're going to get two solutions for L. Just to save some time, so that we can spend more time on the setup, if you do all that number crunching, your two choices turn out to be 22 or 30. Now here you get two solutions, and they're both positive. Now before we talk about our two solutions, is there any question about setting up our equation based on the information given or using quadratic formula to solve that? That look good? Okay, so we got two solutions, 22 or 30. Which one of those two is right? Yeah, here's a case where either one of them is just fine because these are the dimensions of the room. It is 22 by 30 or 30 by 22. We arbitrarily called the narrow one W and the long one L, but we could have switched it around. And so 22 or 30 are our two solutions. When L equals 22, then W has got to equal 30. When L equals 30, W must be 22. And so clearly the room has got to be 22 feet by 30 feet either way. Here's what we've got. You're starting out with a round steel disc, and you're going to chop what's called a segment off of it. Your goal is to chop off a segment or a flat piece off the side of that so that the flat spot that you cut off is the same as the radius. So this value right here is r, and of course some value from the center of the circle to the outer edge is r. Now, it's not enough information to just say what the size of the circle is, because you could do that with any size circle. There's going to be some place to cut it with any size circle so that the flat spot is the same as the radius. We want to do it knowing that this chunk that gets cut off is 1 inch. So now there's only one size circle for which that'll be true, and we want to figure out what it is. Okay? Well, the scenario is a little bit convoluted, but the equation to solve it is actually pretty simple. I'm just going to give you a minute to stare at that and think about what has to be true in this case. How on earth are we going to end up with a quadratic equation? I'm just going to give you a minute to think about that before we go on. No, you're right about the r squared. That's here. Well, 2r would be your diameter. I'm going to put one line on this thing And then I'm going to quickly turn away because all the light bulbs above your head are going to go on when I put this line in right there. Oh, the glare. Because now, what have you got? You've got a right triangle. Okay? Well, what's true about all right triangles? What did Pythagoras say about right triangles? About, I don't know, a few thousand years ago? That's right. We know that a squared, if the two legs of a right triangle are a and b, then a squared plus b squared equals c squared. And we can use that fact to find an unknown side length. The short side squared plus the short side squared, as long as those two are short sides of a right triangle, equals the hypotenuse squared. We can use that fact. Every side, though, is given in relation to r. So here's going to be our quadratic formula. Now we know what the hypotenuse is. That's r. What is this side down here? Half r. Right? Half the radius, because this flat spot is the length of the radius. So this is r over 2. And what is this side? R minus 1, exactly. It's the radius missing 1 inch. So that side is r minus 1. Well, there's your quadratic formula. We know that this side squared, r minus 1 squared, plus this side squared, r over 2 squared, equals r squared. There's our quadratic equation. Well, now we can solve that. Okay? So if we FOIL this out, we get r minus 1 times r minus 1 plus r over 2 squared equals r squared. So FOIL this and we get r squared minus r, that's minus 2r plus 1 plus r squared over 4 equals r squared. Okay, there's our quadratic equation. Let's stop there for a minute. All right, now what do you want to do? Let's get rid of the 4. How do you get rid of that 4? Multiply everything by 4. Clear the fractions. This is, in some sense, a fractional equation because we've got a fraction that we want to clear it out. So we get 4r squared minus 8r plus 4. Again, we're distributing the 4 over every term. It'll cancel only with this one. Plus r squared equals 4r squared. That cleans it up considerably. Well, now you get a little help by coincidence here. 4r squareds are gone. They cancel each other out. There's a set of 4r squareds that cancel each other. And we're left with, let's rearrange that and put it in a logical order. R squared minus 8r plus 4 equals 0. Okay, well that one's a lot less ugly. You could try factoring that one, but I'll tip you off. It won't factor. We have to use the quadratic formula. So r equals negative b, that's negative 8, plus or minus the square root of negative 8 squared minus 4 times 1 times 4 all over 2 times 1. Simplifying that just a pinch and you end up with 8 plus or minus the square root of 48 over 2. Now if you simplify that, we could simplify that algebraically, but we're going to do more with roots a little bit later on. Did you get 0.53? Anybody get the same thing to verify that? Yeah, okay, good. So there they are. Now, you got two positive solutions. They should both seem reasonable, but one of them is not reasonable. Which one do we have to throw out here?
0.536, because that's half of the radius.
Well, the 0.536 is the one that we have to throw out. There you go. We have to have a radius that we can cut one off of and still have something left. .536 is not big enough to cut an inch off of, so we have to throw that solution out. This is the solution for our radius. I forget, did the question ask what is the diameter? No, it said what is the radius of the circle, so we're done. It wouldn't have been too much trouble if it would have asked for the diameter. We just multiply that by 2. Okay, so we found the real solution. Now, what we're going to do is we're going to do a couple more applications in a minute, but we're going to step off to the side. Some applications that you come up with are going to turn out to be fractional equations. In some sense, this one did because there's a fraction in there. But some of them are going to have variables in the denominator. So let's take a minute before we do some applications. Let's just solve a couple of fractional equations that have more than one solution. We're going to do 2 of these before we hop back and do 2 more applications. Okay. Well, nothing new. We just haven't seen it for a few days. You got a fractional equation. What's the first thing you need to decide on? You got to decide on a common denominator. What is your LCD here? 5t. So we're going to multiply every term by 5t. That'll clear off our fractions. Okay, the first term, the t's cancel, and we're left with 5 times t plus 2. Equals, over here, 6t squared plus 5 times t minus 4. Okay. No, see, you didn't know it, but all the fractional equations you were doing before were fixed up. They were rigged so that you never ended up with any squared terms when you cleared the fractions. Okay? Now, by choosing the LCD and doing all the multiplication, if we hit a squared term, we know what to do with it. Well, there's our quadratic equation. All we need to do is solve it. So let's distribute and collect terms. We got 5t plus 10 equals 6t squared plus 5t or minus 20. Is it right this time? 5t plus 10 plus 16. Better? Okay. Shift everything to the right. T squared minus 30 equals 0. Now, here's a case where the quadratic formula is probably not the most efficient way to do this. How do you want to solve that? And let's just shift that 30 to the other side, divide by 6, and take the square root. Okay, when there's no b term, it's a pure quadratic. So if we bump that 30 to the other side, we end up with 30 equals 6t squared. We're using the property of square roots here. (30) is 6t squared. Divide both sides by 6. And we end up with 5 equals t squared. So what's t equal to? The what? Plus or minus square root of 5. That's right. And we're done. We could find the decimal equivalent of that. That's no trouble. We'll just leave it right there. So it can be square root of 5, positive or negative. Now, you would have gotten that result using quadratic formula. It would have just taken a lot more writing. If you don't have that b term, you can just solve it as a pure quadratic. So now we got to check, though. I mean, this one's pretty easy, but we got to check. Does this violate any of the restrictions? Go back to the original equation. What's our only restriction on t? 0. T can't be 0. No problem there. T can't be 0. Well, our solutions weren't 0. It's no trouble. All right. Well, you need 2 to begin with. Right. We got to find our LCD, and you can't really do that till it's factored. Just to save a little board space, because it's kind of limited here for a problem like this, I'm just going to rewrite this factoring that out. Okay? X squared plus 1 well, I just told you. X squared plus x factors into? There you go. Okay. Save a little space. We'll just rewrite that factored out. Okay, well now you can see that your LCD is x times x plus 1. X times x plus 1, right? Yeah, okay. Let's multiply everything through by x times x plus 1. So here we're going to multiply by x times x plus 1. Here we're going to multiply by x times x plus 1. And over here we're going to multiply by x times x plus 1. So the term on the far left becomes x. This term becomes minus x times x plus 3. Don't lose that negative sign. And our last term becomes four x times x plus 1. There's our quadratic equation. Now we just need to solve that. Okay, well, distribute and collect terms. We've got x minus x squared minus 3x equals 4x squared plus 4x. Let's shift everything to the right. Okay, there's our quadratic. Now, based on the quadratic that kind of shook out of that, what method do you want to do to solve that? What method do you want to use? Factor it. Right, there's no C term, factor it. It'll factor very easy. Even though you could use quadratic formula, it's not worth the effort. Factor that. How does it factor? X times 5x plus 6. Okay? So we have two solutions. Either x equals 0 or 5x plus 6 equals 0. Now if we solve this one, we subtract 6 from both sides and divide by 5, and x will be equal to negative 6 fifths. Okay, so we have two solutions, 0 or negative 6 fifths. We still need to check that against our restrictions. Are either of those going to be a problem? Yeah, unfortunately. Go back here. Your restrictions on x from the first term are 0 and negative 1. From this one, they're just negative 1, and there's no restrictions here. So 0 is a restriction. Since 0 is a restriction, we have to throw it out and say that x equals negative 6 fifths. That's not a restriction. We're done. Okay. The driver of a city bus learns that if he drives 80 miles per hour faster than normal, he can cover his 6-mile route in 30 fewer minutes. And the question is, how fast does he normally drive, if that's true? Now, that's a mess of information. That is a mess of information. But if you know one fact, it sifts out real quickly. Distance equals that's the fact that will make this shake out really nicely. Okay? All these word problems that involve a rate, and there's going to be a couple of them in your assignment, they all hinge on this fact. And these are all set up almost exactly the same way. Okay? We'll do another one after this, and it's set up very similar. Setup. Okay, so distance is equal to rate times time. So the first thing we figure is, okay, what's going on when he's not speeding? When he's just doing his normal route, we say that the distance, what's his route when he's not speeding? When he's not speeding, his distance, 6, is equal to, do we know his original rate? Let's just call it r. And do we know his time when he's not speeding? No, when he's not speeding, let's just call it that's his time when he's not speeding. So let's just say r times t. Okay, now let's redo it when he is speeding. How far does he travel when he is speeding? Same distance, okay? He's still got to cover the same route. What's his rate when he is speeding? R plus 80. It's faster, 80 miles per hour faster than his normal rate. Doesn't say he's going 80, but he's going his rate plus an additional 80 miles per hour. So that's his new rate. And what is his new time? Now, it would be t minus 30, except the units are in miles and hours. So it's 30 minutes. We better treat that as being in hours. Okay? So t minus 0.5, noting that 30 minutes is equal to a half an hour. Our rate is in miles per hour. Our distance is miles, so our time has to be in hours. We have to have some consistency to that. You'll have to do that same assumption when you're doing the homework, that your time will have to be in hours to match the miles per hour, and the distance will have to be in miles. Okay? All right. Well, the last thing that we need, this here again is technically a system of equations, but we can use this top fact, 6 is equal to r times t. We want to make a substitution, so we can from this draw this conclusion. If 6 equals rt, what is t? 6 over r. Now we pop that into here and we've got a quadratic equation. 6 equals r plus 80 times, not t anymore, 6 over r minus 0.5. That's the equation we want to solve. You can flip it the other way too. The reason I did it this way is because the question asked, how fast does he normally drive? Or in other words, what's the rate? So I'll get rid of the t and I'll solve this for r. You could have solved for t and then you'd have to go back and find r, and it would work okay. So let's stop there for a minute. That's the trick to this one. Now we just solve it like we did the previous one. 6 equals rt. That means t equals 6 over r, and we can substitute that in. Okay, so we have 6 equals, we need to FOIL this out. R times 6 over r, our f term, 6. Outside, r times 0.5 negative, negative 0.5 r, plus 80 times 6 over r, (480 over r). 6 times 80 is 480 over r. And our last terms, 80 times negative 0.5 minus 40. Okay, now what do you want to do? It's a fractional equation. Technically, it's not a very tough fractional equation, but it is a fractional equation, so what do you got to do? Multiply everything by r. Clear your fractions. So we're going to multiply everything by r. Multiply the left side by r and the right side by r. We get, what's that? You can. You can. I didn't do it because in just a minute we could have canceled off the 6's right here too. We're going to have 6r and 6r in just a minute. They'll just fall right off. But you could combine them. So we have 6r equals 6r minus 0.5 r squared. This is the only one where the r cancels. Plus 480 minus 40r. There's our quadratic equation. Now the 6 r's will cancel off. It's negative 0.5 r squared minus 40r plus 480. I don't want to cause additional confusion. We'll just leave it just the way it is. It'll work out okay. Okay, well, let's just note. I'm going to have to jump back up here for a minute. Gosh, I need to erase that. Let's just note down here that A is equal to negative 0.5. B equals negative 40. And C equals 480. Now when you plug that into your quadratic formula, you get R equals plus or minus the square root of b squared minus 4ac simplifies. I'm just going to save a little room and time here, and that simplifies to 2560 over 2a, which is negative 1. And if you do that, r works out too. We get two solutions. Negative 90.56 or 10 point, I missed a digit there, 90.596 or 10.596. Well, it creates an interesting scenario. We got two solutions. Which one of them do we have to reject, I suppose? You have to reject the negative one, or assume that the bus driver could have been going negative 90 miles per hour in reverse before he increased his speed. But we are assuming we can only have positive rate. So originally he only travels at about 11 miles per hour. He has to get up around 90 miles per hour to shave half an hour off his route. Could be tricky.